Okay, well, I think we should get started. Welcome to Black Hole PIRE webinar. This is webinar number 4 on model comparison. I'm Jeff Bauer. I'm the EHT project scientist, for those of you who don't know me, and I'm serving as the moderator today for this panel. Or for this webinar. The webinar will last about an hour. Thank you very much for coming, and I hope it's fruitful and of interest to you. This is, as I said, the 4th in a series covering the fundamentals of EHT analysis. As you may know, this was intended as a lead up to the summer school that the PIRE project had planned to be held in Mexico this summer. As a result of the pandemic, that will need to be rescheduled. There will be a new set of webinars scheduled starting in August, so look for that coming. You can find all the past webinars on the Black Hole PIRE Science channel, and I see Rosie, I think, has put the link for that in the chat. It's on YouTube. We do ask that you fill in a short poll at the end, a short survey to provide feedback on this series so that we can continue to improve them. Just a couple of general things for smooth functioning of this webinar. Please turn off your audio to limit background noise. Here in Hawaii, roosters and frogs. And birds. Turning off your video can improve the bandwidth. We'll have the schedule will have about 45 minutes for Dimitrios's presentation, followed by a 10-minute question and answer period in which you can put your questions into the chat, and we'll moderate that discussion. So without any further delay, let me introduce our speaker today. Dimitrios Psaltis is professor of physics and astronomy at the University of Arizona. His research group has led the development of tests of the theory of general relativity with EHT observations. He served in extraordinary fashion as EHT project scientist through the 2017 observations and the 2019 announcement, and so has done incredible service and contributions to the project. He's an expert in developing computational tools to study astrophysics of black holes and neutron stars. And today he's going to tell us about model comparison and Bayesian techniques. So welcome, Dimitrios, and the floor is yours.
Thank you very much, Jeff, and thank you for the kind introduction. I hope the audio and the video works. And let me share my screen. Okay, so good morning, everybody. Good afternoon, good evening, wherever you are around the world. And it is my pleasure to present today the 4th in this series of Black Hole PIRE webinars that, as Jeff pointed out, introduces the basic concepts of analyzing and interpreting EHT observations and data. And today we're going to talk about Bayesian model comparison. And before I move on, I just wanted to give 3 references for additional reading. This is only 45-minute webinar, and unfortunately we will not be meeting this summer for a few days in Mexico, where we could have explored all of those issues in a lot more detail. But if you want to look a little more into it and do some more reading about general Bayesian model comparison, these are my 3 suggestions. First one is the website of a graduate level class in statistical methods in astrophysics that I teach at the University of Arizona. And in there you will find links to many places to look for, like papers and review articles and textbooks that you can explore some more of those issues. The Penn State University Center for Astrostatistics has a wonderful page. They also organize regular summer schools, and they have all their lecture notes online. So this is the second link. And the third link is a single review paper called Data Analysis Recipes. It is from the NYU group in New York. And if you were to read one paper about how to fit models to data, I would suggest that this is the place to start. And the previous 3 webinars have given us a lot of provided a lot of input on how the Event Horizon Telescope and in general an interferometer works, how we collect data and how to use them to generate images. So I will not go into any of that, but just in case somebody has not gone through those previous webinars, I just want to give a 2-minute introduction of how an interferometer works, actually what the measurements really are, because this will turn out to be important for the way that we're going to analyze them and try to fit models to them. So fundamentally, an interferometer is a collection of telescopes, a collection of arrays. And if you had just 2 of them, say one in Chile here and one in Spain, what you would do is you would take the voltage out of those 2 telescopes, correlate them, and measure the complex correlation between those 2 voltages. It turns out, by a wonderful theorem, that this correlation that you will measure is nothing but the complex component of the Fourier transform of the image of the source in the sky that you're trying to measure. If you think on the right, this is the Fourier map of the source image. The component that you're measuring is at a location that has an orientation parallel to the baseline that connects your 2 telescopes, and a frequency equal to the length of that baselines in terms of the wavelength of observation. Now, of course, if we just had 2 telescopes and we did 1 observation, then we would get a single Fourier component, frequency component of the image. We wouldn't be able to generate an image. We wouldn't be able to fit any models to the data. But what we do is that we put more telescopes and we wait for the Earth to rotate. And as the Earth rotates, all those baselines provide a different projected length and different orientation on the plane of the sky. And as you wait for the Earth to rotate and you see North America coming inside, Hawaii coming inside, then you slowly fill that Fourier space that we call in this particular field the UV space. We call the horizontal frequency the U coordinate, the vertical frequency the V coordinate. So that's why we often call it a UV space. So fundamentally, our measurements are in Fourier space, and this is the measurements that we had from 2017 for the M87 observations. On the left, you see the coverage. These are all the blue, purple, whatever colorful line segments that show the baseline paths traced by different pairs of telescopes. So this is where we have the data. For each one of these data points, we have a complex number, the complex correlation. And if we plot the amplitude of that complex number as a function purely of the radial distance from the center of the Fourier space, so we collapse this 2-dimensional space into 1-dimensional, the magnitude of the spatial frequency, then this is what the data look like. And they have this characteristic ringing, which is a signature of a compact image, something that we have resolved. And as I will show in a second, we can more or less quantify its size and its characteristics. So these are the kind of data that we have, different frequency locations in Fourier space and different amplitudes and phases that we want to compare theoretical models or model images to. And why is that going to be fruitful? So this is a very quick demonstration of how the data in Fourier space have a number of characteristic features, we call them the salient features, that effectively determine most of the properties, most of the characteristics of the image. To give you an example, the right-hand side here is the exact same data points that I showed you before, the M87 observations of 2017. visibility amplitude as a function of baseline length, and the red data points are here. If we were to have an image in the sky that was just a uniform disk with this characteristic size, I don't know what is it, maybe 25 microarc seconds, and I were to take the Fourier transform of that image, that will just be a simple Bessel function. And this is what it would have predicted. And clearly that's inconsistent with the data. How do I need to manipulate the image to make it consistent with the data? Well, the size of the image determines the location of that first deep minimum in visibility amplitude. So by increasing the size of the image, I can shift that visibility minimum until I get the location of that first minimum, which determines the image diameter. But what you see is that the Fourier transform of a filled disk has a secondary maximum that is much lower in amplitude than the data. And it has a secondary minimum that is in a place where we have significant observation, significant visibility amplitude. What do I need to do to the image in order to account for that? Well, we start putting a hole in the center of the image. And by turning the image from a disk to a narrow ring, then not only do I get the right first minimum, I get the correct, more or less, secondary maximum, the location of the secondary minimum, and so on. And then I can start introducing some blurring, which is going to start moving the images. I can start introducing asymmetries and so on. So this is a by eye and manual fitting of a model to the data. But what we really want to do, the goal of model fitting, is to formalize the procedure that I just described heuristically, and more importantly, quantify the best fit model parameters and their uncertainties. What is the best fit size? What is the best fit width? Perhaps asymmetry, perhaps location of other places in the characteristic features in the image. Now, you might think these are the data points. They look pretty straightforward. The models that we're trying to fit often are very simple. Crescent disks, rings, differences of Bessel functions, maybe Gaussians here and there. So it should be straightforward in this day and age to download any, model fitting MCMC algorithm for Python and, plug in your model, compare it to the data, and get the best fit result. What is there to talk for another 35 minutes in this webinar? Why are we keep on discussing it instead of just applying it? So the goal of this webinar is twofold in my mind. One is to introduce the fact that what we are doing fundamentally in this field, actually most other measurements in physics, is a Bayesian model comparison. It's not a frequentist model comparison. We won't be using chi-square fitting. And this is something that has to do with the particular way that we make measurements and we infer the uncertainties in those measurements. There's a very beautiful paper, it's mostly philosophy of science than science itself, by Robert Cousins 25 years ago, that says, why isn't every physicist a Bayesian? And what he says is that it's about particle physics, but applies to astrophysics as well. Many other particle physicists may frequently think in a Bayesian manner without realizing it. So my first goal for this webinar is to demonstrate that the model comparison that we're trying to do is fundamentally a Bayesian process, and that informs what kind of tools we will be using in order to do the model comparison. But the second and more important goal of this webinar is to understand not only the fundamentals of statistical modeling, but also the pitfalls. We need to be able to know under what circumstances the results that we're getting from such a fitting are not appropriate, are not correct, or they're misleading, they're biased, to avoid getting fooled. And this is something that has been is being explored in many applications of statistics. Applied statistics actually devotes most of its time right now in these kinds of issues. There's a great paper written in Nature primarily about biostatistics that's called How Scientists Fool Themselves and How They Can Stop. And the tagline is that many researchers seek ways to fight their own worst instincts, which is people are remarkably good at self-deception. We get results out of very complex statistical inference models, and we are very prone to believing them. So what I would try to do with this webinar is try to point out all the unique challenges that have to do with VLBI model fitting and how to generate strategies to avoid getting fooled from the results that we're going to get. So let's start at the very beginning. Why do I say that VLBI model fitting is fundamentally Bayesian? And to understand that, let's ask ourselves generically in physics, whenever we do any measurement, how do we implicitly make the measurement and how do we assign errors? So this is a very generic example. It's actually from Wikipedia. You measure a particular quantity, it doesn't matter what you mean. And what we often think we do is that we make a very, 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 very large number of measurements. Each measurement will come with its own statistical error, so it's thermal noise, as we say in VLBI. And then if we plot it, that measurement will have a particular distribution, and we're going to quantify what is the most likely value of the measurement and what is the uncertainty, right? This is what we usually think that we do when we make a measurement. However, this is not what we actually do when we make a measurement, right? When we make a measurement at any particular spatial frequency, at any particular time with the Event Horizon Telescope, we make a single measurement. We don't go back and repeat it in an independent way. We don't go back and reproduce the measurement the next day, like for hundreds and thousands of times to quantify that measuring uncertainty. Instead, if we were to do it, it would have been trivial, because there is something called the central limit theorem that tells us that if we make a very, very large number of independent measurements, then we don't have to worry about errors. The central limit theorem tells us that the peak of those distribution of measurements will be the true value. But as I said, we never do that in physics. What we do is we make a single measurement. April 5th, 2017, we turned the telescopes at 5:13 p.m. Eastern time, and we took one snapshot, one set of measurements for that particular orientation of the telescope. And then we assign an uncertainty to that measurement based either on calibration. We have used the telescope to observe other sources of known properties, and we have an idea of how well the telescope works, or based on a physical model of its performance. We make a model of the telescope itself, the atmosphere, anything that can go through, and we estimate what is the degree of error that our measurement is going to make. And in fact, with the Event Horizon Telescope, as Lindy talked about in the second VLBI, we do both. We do actually a combination of physical calibration and calibrating measurements. And why is that different? Well, the trickiness, the difficult comes when the uncertainty distribution that we're going to measure is asymmetric. Sometimes we overestimate more than underestimate and vice versa. And more importantly, when there is a bias, when what you measure is not peaking the distribution of measurements on what the true underlying quantity that you're trying to measure is. And of all things, actually, radio astronomy and interferometry in particular is the prime example of why that is complicated. This is a plot that I picked out of the TMS book, the Basics of Radio Interferometry book, that shows, given a true value, suppose that you knew that your source gives a particular visibility amplitude, here is normalized in terms of its error at a 5 signal to noise ratio, what would have been the distribution of measurements that you would make? This is the physical model that I talked about of telling us what the performance of the instrument is. And when that signal to noise ratio is large, then the distribution of measured values is indeed peaking at the true value, 5, and it has a width that is comparable to the signal to noise ratio of the true measurement. But as you go to smaller and smaller and smaller intrinsic values of the quantity that you're trying to measure, especially when you have zero visibility to measure, there's nothing, the source does not emit anything at that particular baseline length that you're observing, you still have a distribution of measurements that you're going to make, which is nothing but your thermal noise, right? And that distribution is asymmetric. This is a well-defined distribution for purely thermal noise. It's called the Rice distribution. It is not symmetric. And as you can see from at the low signal to noise ratio, it does not peak at the true value. So even if you were to make an infinite number of measurements, your most likely measurement would not be the true value of the source that you're trying to detect. In fact, what this distribution is the opposite of what we really want to know. This distribution tells you what the distribution of measurements would be if you know the true value of the that comes out of the source. If you know the true value of the visibility amplitude, this is what you measure. However, we want to know the exact opposite distribution. We want to know, if we know the measurement, what is the most likely true value that came from the source? Exactly the opposite. And in other words, our calibration allows us to place error bars in our model predictions. If this is the model prediction, this is what the error bar of the measurement, and not in the measurements themselves. So every time you see a plot that has error bars, what you're implicitly saying, like the plot that I showed you earlier, what you're implicitly saying is that this is the value that I measured, whatever your dot of your point is. And if the underlying source, if the underlying true value, the ground truth value was that, then the error bar would give you the range of uncertainties of the measurement, as opposed to what we often think that error bars tell you, which is, this is my measurement and the true value lies somewhere within that error bar. And this example, when you go to the zero signal to noise ratio, demonstrates why the two are actually not the same. And there's actually another very common example in applied statistics given from everyday life that tells you that demonstrates that those two expressions are not the same. What is the likelihood of a measurement giving the true value is not the same as what is the true value given, what's the likelihood of the true value given a measurement. And the example that is often given is, let's say that I have a herd of, say, 100 horses. 50 of them are male, 50 of them are female. And some of the female horses are pregnant. Then I ask myself, what is the chance that of all the female horses, some are pregnant? You can calculate that. You know, if 2 out of the 50 female horses were pregnant, the chance is 4%. But that is very different than of all the pregnant horses, what is the chance that one of them is female? Because that's clearly 100%, right? All the pregnant horses are necessarily female. So flipping the order of, in conditional probabilities, of the condition to the quantity on which you want to make the probability of is not the same. One is not equal to the other. And very often in this field, in especially VLBI, you will see something called debiasing. You try to go from the first quantity, which is what you really can quantify, to the second quantity, which is what you really measure. And the idea is that you're going to subtract from one the thermal noise, and that will give you the second. Well, this is kind of unfortunate because not only does it hide the true fact that these are fundamentally a Bayesian measurement, but perhaps more interestingly is that the correct way to go from one to the other is actually substantially simpler, both computationally and conceptually, than debiasing, and introduces no errors. And that has to do with Bayes' theorem, right? What you want is you want a probability of B given A, but you only measured the opposite. So how do you combine them? Well, what you do is you calculate the probability that both A and B, both events, are simultaneously true. And you calculate it 2 ways. One is you say, what's the probability that both A and B is true? Well, it's the probability that A is true times the conditional probability that given A, B is also true. This tells you the chance that both A and B are true. But I can do the same calculation by flipping the order. The conjoint probability is the chance that B is true, and if B is true, A is also true. And those 2 left-hand sides have to be the same. I equate the 2 left-hand sides, that means the right-hand sides are the same, solve the problem, and I effectively just proved Bayes' theorem in 1 line. The chance that A is true if B is true is equal to the chance that B is true given A times the ratio of prior information about A and B. And that's all there is to it. There's no debiasing, there's no subtraction, there's nothing. Those 2 probabilities are connected by just a ratio of priors. And if you call A your chance that the model is true, and if you call B the data set that you measured, the likelihood that a model, particular model is true given the data, is equal to the likelihood that you made this data observation given the model times the prior in the model divided by the prior in the data. What then you end up doing is you have to normalize this so that this posterior, this probability has an integral of 1 that cancels out this denominator, and effectively this is what we have to deal with. What we really care about, the probability over all the model parameters given the data, is a normalization constant times the likelihood. What is the chance that I would have made those data observations given the model? And this is just the product of all those Rice functions that I know how to calculate times the prior for the model. How do I realistically think, how realistic do I think that this particular model is? And a little bit of terminology, this last quantity, we call it the prior on the model. What you really calculate, all those Rice functions and so on, we call it the likelihood for the model. And the final result, we call the posterior probability of the model. So this is all we need to do. Given a set of model parameters, I need to calculate the chance that I make this particular set of data models, multiply it, and then use a technique, say Markov chain Monte Carlos, direct integration, sampling, whatever you want it to be, explore the posterior, find out what is the set of parameters that has the maximum posterior and what is the range of parameters that give a posterior good enough for me, whatever that good enough is, 68th percentile, 90th percentile, 95th percentile. And this is a very simple multiplication, nothing more than that in sampling. So, but the reason that I call it famous last words is that this is where the difficulties start. This is basic of Bayesian inference. And the differences come in for a number of reasons that have to do with the special challenges of the VLBI data. And one of them is that the calibration of our measurements is not perfect. I talked about the Rice distribution when the only source of uncertainty and noise is just thermal noise. But in principle, we have unaccounted calibration errors that in general, we call them the gain of a telescope. And of course, has to do with the telescope and the atmosphere above it. And mathematically, the way to write it is that if you have at a particular location, UV space, if you have a true value written here by the calligraphic V of your model, what you really measure before any errors, thermal errors, has to be multiplied by those two gains that has to do with telescope I and telescope J that contribute, that are part of that baseline. And the reason that one of them has a complex conjugate here is because you want the resulting visibility, of course, will be a visibility of an EL image such that the conjugate of that visibility has to be equal to the negative of this visibility on the right. So this is just a mathematical reason why we put that there. How do we account for that? Two ways. One way is that you can define what they're called closure quantities, which are ratios of visibilities between different baselines defined in such a way that those complex coefficients cancel. I will come to that as number two. But number one is that you can incorporate those gains into your model. So your model, this right-hand side, the true value, will not depend only on the underlying parameters of the model, the size of the image, the degree of depression, the orientation of the image, but will also depend, the model predictions, on exactly how the telescope behaves. You might say, by doing that, then I lost any control of my predictive power of the model because I can move those gains up and down to get whatever I want. That's not entirely true because, as I said, the calibration is not perfect, but we know the values of those quantities to a large degree. We just don't know them perfectly enough. And to give you an idea at what level we know that for something like the 2017 EHT observations, this is from the third paper of the Event Horizon Telescope. To the left, you see the various stations, the various telescopes in Chile, Chile down here as well, and various parts around in the sky. These are various contributions to the calibration that I believe Lindy talked about, I will not have time to discuss here, but if you look at the last column, you see the percentage error budget that goes effectively into those gains. Some telescopes we know better than others, but we cannot move those gains infinitely up and down. We still have to be constrained by the accuracy of the calibration, which is of the order of 10, 15, 20% maybe from telescope. So when it comes to using the amplitudes of those visibilities, it is very useful to actually model the gains as part of your model itself, subject to the constraints of the error budget of the a priori calibration. But that's not the case for the phases, the complex phases of the visibilities. The visibilities, as I said, are complex numbers. The reason being that we really have no constraint yet of the uncertainty in those individual complex phases. Actually, they can be circling around 0 and 2 pi really rapidly because of the turbulent atmosphere, and we wouldn't know. But we are not throwing that information away either, because what we do is we can calculate what they're called closure phases, closure products, for which all those gains are canceled. And I believe the previous two webinars introduced closure phases as the sum of the complex phases along the three baselines of a triangle, closure triangle. The other way to do it, which is equivalent, is a closure phase is the complex phase of the bispectrum, the triple product of the visibilities along a closed triangle. So if I take three baselines that close, so ij, j, k, and then circle back to ki, and take the argument, the complex argument of that triple product, you use the expression that I've given you before with the gains. Because every telescope appears in two baselines, you get both the gain and its complex conjugate. That product is just the magnitude of the gain squared. This is a real number. It has no phase, no complex phase. This whole first term goes away. And therefore, the argument of the bispectrum, the closure phase that you measure, is identical to the true argument of the bispectrum, and all the gains have canceled away. So this not only cancels away the gains, but also cancels away the uncertainties. We do not have to model gains. We do not have to quantify their uncertainties. We clearly lost some information, and how the degree of information you lose actually reduces the more baselines that you have. But this is the way that we have, because there's nothing better than we can do about it. So modeling the gains, incomplete coverage of the incomplete calibration of the telescopes, and the fact that we have to use closure phases introduce additional challenges to VLBI model fitting. The uncertainties of the closure amplitudes are straightforward. There are Rice distributions, and it turns out that they're extremely fast numerical algorithms to calculate Rice distributions, so that's never a problem. Using closure phases, though, introduces an additional challenge with two additional challenges, which is, first of all, the distribution of errors, that predictive likelihoods that I was talking about before for closure phases, are very difficult to compute numerically, especially at low signal to noise ratios. They're not Gaussian. And one of the main reasons, of course, is that phases are circular quantities. And as the Gaussian, if it were Gaussians and the Gaussian keeps on broadening and broadening and broadening, you have to chop off that Gaussian between 0 and 2 pi. And then at some point, you're losing a big part of what you thought was your posterior. And to give you an idea of how they look like, this is not a closure phase. This is the phase of one of the three baselines of the triangle. And you actually have to convolve numerically three of them. Signal to noise ratio of 1.5, low signal to noise ratio. The red line is a Monte Carlo simulation of what the error bars, the uncertainties in that single phase is. And the green and the black lines are the Gaussian approximations to the phase for that signal to noise ratio. And you see the width and the shape of the Gaussian approximation at low signal to noise ratios are very inadequate. At the limit of very high signal to noise, they both match. Now, on top of that, you need to be able to take three of them and convolve them, cross-correlate them, and that becomes a very complex three-dimensional integral. Thankfully, recently, we came up with a very efficient numerical algorithm to do that, and actually use in our numerical techniques the complete distribution of uncertainties for closure phases without having also to make this Gaussian approximation. The second challenge is the fact that because different triangles of bases share same baselines. You can have a triangle with 3 baselines and then a triangle with another 3 baselines, but sharing one, which is what we usually do. The correlated errors between the triangles are actually quite complex and how to calculate them. Say the off-diagonal matrix of the covariance of the closure phases. And this is very difficult to do numerically, but there's a nice paper by Lindy Blackburn and collaborators later last year, where they show that when you have an array like the Event Horizon Telescope, where the signal to noise ratio is very different from station to station, then there's actually a smart way of identifying those triangles in order to reduce as much as you can the complex correlated errors. And that allows us to make progress with closure phases, even though numerically are very difficult to handle. And last challenge, which it will become obvious why it is a challenge in a little bit, is the fact that the Event Horizon Telescope, like most VLBI arrays, are very sparse. You know, most of the Earth, we need the entire Earth. We need to place telescopes all around the Earth. Most of the Earth is ocean. We have enormous patches of the Earth that we cannot put telescopes on. And therefore, when you look at the coverage in Fourier space of where we put telescopes on, you see incredibly large patches of emptiness. And actually in 2017 observations, we had 2 main orientations, the blue and the red orientations, where we had telescopes. The red orientation is north-south. That is primarily the telescopes along the Americas, in Arizona, in Mexico, and in Chile, and all the combinations. And the telescopes in the orientation east-west are the telescopes that primarily line them near the tropic line from Hawaii to Arizona and Mexico and to Granada, and they're primarily east-west. That's why you have these 2 basic orientations. And the reason that this is challenging will become obvious in a second. So a lot of background, a lot of interpretation, a lot of expectation. Let's see how it works in practice. So this is a very, very simple problem. I just generated synthetic data for the Event Horizon Telescope, assuming that the source in the sky that you would measure is nothing but a ring, nothing else, no complexity whatsoever, has a radius equal to that what we found in M87, and a small fractional width. It's a 10% ring. Not only that, but I made all the telescopes give the exact same, all the baselines have the exact same signal to noise ratio, 10%. And this is the data that it generated, just to make sure that everything works the way that we expected. And because, of course, I tried to fit those data with a similar model, the model that in principle allows for asymmetric crescent, but one of the possibilities is a perfectly symmetric ring, I have a beautiful fit with residuals that are completely consistent with the thermal noise that I introduce, right? So in principle, that works. And what you see here is the posterior, the confidence, the credible intervals between the radius and the fractional width of the model that comes out of this expression, this equation. And the ground truth parameters were 21 microarc second and 10% fractional width, which would be where my pointer is right now. Now, one thing that you see immediately is that there is an anti-correlated behavior between the radius and the fractional width. And this turns out to be nothing but what's shown here in the red line, which is the locus, the combination of widths and radii of models that make the first minimum, as I showed in the very first animation, equal to the location of the minimum that comes out of the data. So in other words, everything on this red dashed line would generate the first minimum here at about 3.25 gigalambda, which is why you can shift the data around because of thermal noise, but effectively you'll have to follow that correlated uncertainty. This is how we understand those correlated uncertainties. But let's pay a little more attention to this, the posterior, the error bars that we get out of the radius. What you would see if you look even by eye what the range of uncertainties is that the radius of the image is extremely well determined. It turns out to be determined with an uncertainty of 0.1%. And this is unexpected, too good to be true if you wish, because we had used 150 data points. That's how many we have. And by the way, it's not only the amplitudes, but also the closure phases that I didn't use here. Each data point had a 10% uncertainty. And if you were to use the normal expectation of, if it was a linear model, like a least square fit to a line, what would the uncertainty in the radius be? You could expect it to measure it to within 1.5%. And yet our Bayesian analysis gave us better than a factor of 15 in the uncertainty of the radius. Why did that happen? Well, the reason is that the model that we're trying to fit to the data and the behavior of the data is very far from being linear. And to quantify that, I show you here what we call the sensitivity of the model, which affect as a function of baseline length. And those curves, one is the sensitivity on the radius of the model, and the dashed red line is the sensitivity of the fractional width of the model, tell you how much does the model prediction change given a small change in the model parameters. When this is 1, here, the horizontal line at 1, it means that if I change the model parameter, say by 1%, the prediction at different baseline lengths would also be different by 1%. And what you see is that instead of, that would have been in the case of a linear model. Instead, what you say is that our model predictions have very high sensitivity based on baseline length. Those big peaks are the location of the minima, and the big troughs are the location of the maxima, which means that here it's going to be about 10 to the minus 2 at 6 gigalambda. What that implies is that if I change the model by 100%, like double the radius of the model, the prediction for that data point at 6 gigalambda will change only by 1%. And therefore, I won't be able to see it given my error bars. On the other hand, if I am at the minimum, the location of that first null, or the second null for that matter, I can change, it's here say 100 for the radius. I can change the location of the size of the ring, the radius, by 1%, and that will change the model prediction by order unit. It will double the prediction of the model, which will be clearly seen given my data. And what that means is that the model parameter, the inference of the model parameter depends very sensitively on the exact measurements that you make at the location of that minima, which was this idea of the salient features that I described earlier. And there's actually a way to quantify it. It's called the influence, the Bayesian influence of various data points. This is for the example that I gave you before. This is the Bayesian influence of all the other data points, relative influence. And this is the Bayesian influence of the data points near the minimum. And you will see that there's a factor of 100 to 1,000 more influential in determining the parameters of the model than all the other models are. It is that factor of 100 or 1,000, if you take square root of that, you get about a factor of 30, that is the cause that the radii that we infer from the Bayesian inference, from the model comparison, are so much better inferred, have so much smaller error bars than what normal model comparison would let you believe. And as I said, data points near the visibility minimum exert disproportional influence. And you might say, this is great. I just need to measure those points really well, and then that will allow me to constrain the model parameters extremely well. But that would have been the case if and only if my model was a perfect description of the data. We don't really think that our data are just simple crescents, flat top with maybe a little bit of Gaussian curvature, right? Gaussian smoothing. These are meant to be approximations to the underlying image. And if the approximation at that location of the minimum is not good enough, that disproportionate influence that that data point will have will bias what I infer afterwards for model parameters. And just in case you were wondering why was I paying so much attention earlier about getting the uncertainties, the error bar, and the predictions of those low signal to noise ratio cases, Well, it turns out that, as expected, the most influential data points are the ones near the minimum. Here I added 10% error bars everywhere, but in reality, these are the data points that have such a low visibility amplitude that they're barely detectable. They have very low signal to noise ratios. So getting the signal to noise ratio uncertainty for the low SNR data points correct will make an enormous difference in constraining the influence of those data points on our model comparison. The second thing that comes out of that very simple exercise is that even though I fit the data with a perfectly symmetric, I generated synthetic data with a perfectly symmetric ring, when I look at my distribution of best fit models, this is the orientation of the blue and the red baselines, I actually get rings that point somewhere between the blue and the red lines. My model much prefers rings that are asymmetric and lined up with the orientation of those lines. Time is getting late, so I will not have time to describe that in detail why that's the case. It's a direct influence of the sparse coverage of the EHT observations, but this is something that will come up in a second, because what I really want to talk about is, forget that simple model, let's talk about a realistic example. This is a snapshot on the left of a GRMHD simulation that has all the bells and whistles, all the complexities, perhaps even more than the true underlying image is. And here on the middle, on the right of those two, I show the exact same snapshot image, but filtered with a Butterworth filter at the resolution of the detector, because we want to not have the eye drawn to the fact that there's very, very fine structures that our instrument will not have access to. So this is the kind of baseline image that hopefully model fitting will generate. We use that image with all the bells and whistles, generated data. Here are the data on the right, the blue and the red baselines again as before. You see the data have this characteristic minimum here, the secondary minimum, because it's a beautiful ring. We fit it with a crescent model like we do with the Event Horizon telescope. The fit is quite good, not perfect because of the little structures, and the image that comes out of that fitting process is not that different than what the filtered image of the GRMHD simulation is. Similar size, nice big depression in the middle, orientation towards the northeast this way, which is what the underlying image is. So when the data indeed have this beautiful structure, then model fitting works beautifully well. But what if I look at a slightly different, perhaps more realistic example out of the GRMHD simulations? This is another snapshot that has not only that ring of emission, but has this little flux tube that came out in the bottom left that generates this little asymmetry here. Do the exact same thing. The middle one is the filtered one, what you would expect to see. Generate data, fit the data. On the right, you see the generated data, blue and red baselines. Black is your model, really bad residuals. And bottom here is what is the image that you infer by fitting that model to the data that generated from this GRMHD simulation. What you see is that the process completely failed, right? The size is maybe twice as big as what the true size is. The relative width is completely wrong. The orientation is, 90 degrees away. And the reason is, if you look at the data, that the blue baselines do not have this characteristic nice sharp feature that your model has. The red baselines have none at all. And the model is trying its best to go through the structure, but clearly does not have enough freedom to do it. So we might think that, okay, the way to move forward is start adding more structure to the model. So suppose that I add another Gaussian, maybe to this crescent model, maybe to try to simulate and reproduce this little extra thing that happens here. So start from the same model again, the same image, but fitted with a crescent plus a Gaussian. And if you look at the data points now and the model predictions and the residuals, I did much, much better, right? Clearly. But if you look at the best fit image that comes out of that, first of all, you see that again, the size is not right, is about 50% larger. Again, because of the significant issue with the fact that the salient feature is missing. And more importantly, the Gaussian that was added, this extremely elongated structure there, is not in the right place with respect to where the crescent is. And if you actually go through the numbers, you'll realize that the short baseline, the short direction here, which is the long direction in UV space, is aligned with the red baselines, because what this Gaussian tried to do is try to fix the red baselines that were the problem before, and therefore put something there to fix the red baselines where you have the data and not worry about anything else where you don't have the data for. So the sparse orientation made a very significant bias in what this addition of extra Gaussians added to the problem. So I'm almost ready, very last transparency, and then we can have a quick discussion. So how does that work for the actual observations of M87? So this is the plot from one of the papers, the sixth paper of the first EHT results. This is the mean diameter in microarcseconds and fractional width in the y-axis that I showed you before. This is for the true M87 data. Those anti-correlated bands that I showed here, one of them, the blue, is the one that I talked about that has to do with all the shapes that have the first minimum in the right place. The redder one has to do with similar anti-correlations that you get when you Gaussian broaden those crescents. They're more or less the same. The black and the green points are the parameters that you infer from image domain analysis, the thing that Andrew talked about in the previous webinar, and the blue and the red points are the things that you get from directly model comparison analysis to the data. And because we do not require, like imaging algorithms do, to the structures to be larger than some baseline, some characteristic beam width of the image, then you see that in principle model comparison algorithms allow you to find narrower features, narrower widths where they are. This is April 5th, but we had observations in April 6th, and they don't look that different. But we also had observations in April 7th, and we had observations in April 8th. And what you see by looking at the blue and the red points that come out of model comparison is that they actually move around quite a lot, as in the blue data points here go between 37 and 40 microarcseconds on April 11th, whereas on April 10th was between 41 microseconds and 45th microarcseconds. So the, 5th, 6th, and 11th. So this, we don't think, and actually you can see directly in the data, we do not think that this is something that truly happened in the source. The source did not change by 10% in size or 10% in width in those days. What this is different biases because of the location of the influential points and the fact that our model is not a perfect description of the data that you can very well control and explore by repeating observations from day to day to day, which is why we see those bands to be quite wide. It was meant to be from the beginning a degree of the systematic uncertainties in the measurement, even though the formal uncertainties were substantially smaller. And this is why we keep on repeating this observation from day to day, from year to year. So time is getting late. So let me just summarize. I hope I try to convince everybody that Bayesian model comparison offers indeed a very powerful tool of characterizing the basic structures of cosmic sources observed with interferometers. But when it comes to using VLBI data, we have to be more careful than normal model comparison because of the special challenges introduced by VLBI data, the gains, the closure quantities, the fact that we have a non-perfect coverage of Fourier space. The error distributions that you will get by doing this model comparison will be completely dominated by systematics as opposed to the formal uncertainties, but that's not a problem. This is not the first time that that happens in physics and astrophysics. We have ways of dealing with them, and one of them is with synthetic data challenges that allow us to quantify the degree of those systematics, but more and more importantly, repeated measurements. Keep on getting more and more measurements of the same source over different days, over different years, because the different realizations of those images will eventually explore the whole range of systematics. And then at that point, we will be able to do a true frequentist analysis do the measurement in many, many, many different independent ways and use the standard limit theorem to tell what the underlying value is. And I will stop here. Thank you.
Okay, thank you, Dimitrios. Very informative and interesting. Questions or comments, you can write them into the chat, or if you'd like, we can, I believe we can also enable you. Actually, I think if you use the Q&A, that's better, because then those can be visible to everyone. While we're waiting, I'll pose a question, Dimitrios, that had we chosen a purely frequentist approach to analyzing our EHT results, our M87 results, how would the answer have differed?
Oops, I missed you for a second. The data would have been different, right? What you would need to do is you would need, suppose that we picked, let's say standard limit theorem you can reach with 10, 20 observations maybe. Suppose that we observed every single night for 20 days with at the exact same times and took the measurement. And therefore at every place in UV space, we would have a distribution of measurements over those 20 nights. And let's say for the sake of argument that the source didn't change over 20 nights. Then we would have a frequentist distribution of measurements, and then it's just a matter of doing chi-square. So that would have been a very different range of distributions, of measurement distributions, than us assigning rise distributions and other uncertainties and doing Bayesian. So the data would have been different.
Okay. Okay, I think I see your point there.
Yeah, of course it would have been best to do it with 5 different arrays also, because then you need also independent measuring devices, right? So if we had 5 different arrays and 10 different days, that would have been perfect. Yes, well, I think we can all agree that we would like 5 different arrays and an infinite amount of observing time. Yeah, Remu just left the room, so I think I'm glad, that's why I said that.
Yes. Yes. Okay. I'm just looking to see if there are any questions in the chat or in the Q&A. I don't see anything there. Do you want to briefly say something about why there's a preference for particular orientations? I
can show that. Let me share my screen again. So the way that I like to describe that is in terms of something called the projection slice theorem of Fourier transforms. And this is actually the origin, the reason that things like medical tomography works. And the mathematics turn out to be identical to what we do for interferometer. And this is from Wikipedia. And what that theorem tells you is that suppose that you have an image, like this weird shape here, and you put an axis like X in some particular orientation, and you project the image on that axis. And now you take a one-dimensional Fourier transform along that axis. That turns out to be identical to a slice in Fourier space, of the 2-dimensional Fourier space, with an orientation that is parallel to that axis, right? And this is how tomography works, because what they do is that they take different projections of the X-rays as the tomography rotates all around the person's body. Then they take the Fourier transform, and now they have a complete 2-dimensional Fourier transform. They do the inverse Fourier transform, and you get the entire volumetric image of what is behind. But what that means in our case is that because we have primarily 2 orientations, and I have them here, I think, and forget for a second the purple and the green ones, which are just one effectively point in UV space, is we are predominantly measuring the projection of images along those 2 orientations. And therefore, I have a wide volume of possibilities where I make my image to be a little to the left of the red, or a little to the left of the right, or to the right of the red, or a little to the left of the blue and a little to the right of the blue, that has the exact same projection along the blue line, if it's a little more asymmetric than it truly is. And then if I count, when you do the posterior probability over orientations, you count how many ways can you reproduce the data. You have a lot more ways for things that are symmetric around those two orientations than for things that are not. And this is why you get your posterior to be slightly more asymmetric than what the true image is, and peaking in orientations that effectively straddle those two main orientations. This is slightly different than the case of this case, which also is biased, where you see here, the big problem is the red baselines that are completely wrong. You can see the residuals. And the first thing that you will do by one Gaussian by itself will not be able to fix all the problems, but it will fix one problem more. So you want to add a Gaussian that fixes the red without touching the blue baselines. And how do you do that? You make a model that is so elongated that it affects only one orientation and not the other. And therefore, all those extremely elongated structures that you have are just tweaks that you add to fix the model in particular places without affecting it in other.
Okay, good. Thank you.
Mm-hmm.
So I think our hour is up here. I want to thank Dimitrios for a very informative and thought-provoking presentation. This will appear on the YouTube channel, so you can go back and view it for more details. We ask that you fill in the survey. The link to that is in the chat. And with that, we'll wrap up. So thank you, everyone, and bye-bye.
Thank you, Jeff.